Yeah, thank you for the audience. Thanks that you came. Thanks for the Congress for giving me the opportunity to be here tonight, to be able to tell you a bit about post-quantum cryptography, a bit about isogenies. I mean, just educate the people a bit about what that means even, because I'm not so sure how many of you heard about that before. Yeah, let's just jump right in. So, my day job is being a mathematics PhD student at an undisclosed university. You can ask me in private if you're interested. So previously I did physics. I was also, or maybe I'm still a bit active in the console hacking scene. And if you're interested about that, shameless plug, you can find us at the Nintendo Bros assembly later. You can ask us all about our somehow console hacking endeavors. But enough about that. So I brought you some pictures, screenshots of websites. So I don't know if you have seen the chatter on social media and the blog sphere recently about that Google paper on quantum supremacy. So there's a Nature article about that, beyond quantum supremacy, and there is a Verge article that Google confirms quantum supremacy, a breakthrough, whatever that means. There is Google's own blog post about it. Notice there are always these shiny pictures of these huge tubs filled with helium where they house these quantum computers. So supremacy means the state or condition of being superior to all others in authority, power, or status. So calling something quantum supremacy, I mean, that screams of something being pretty amazing. But what actually does this mean for us? What does it mean for cryptography? And I think I can relieve you all about from maybe some fears that you had. For us in practice, maybe today, it doesn't really mean anything yet. So for cryptography, none of our underlying assumptions, whatever that means for now, are being actively broken yet, as we know of, or that we know of. But in theory, they are broken, okay? And because they're only broken in theory, that's very good, so we can still blame the designers and the implementers of whatever we cook up for when things go wrong, so that's nice too. But, as I already wrote in the abstract a bit for this talk, we should be somehow better be safe than sorry. So instead of somehow waiting until the point of where quantum computers somehow become feasible to break our cryptography, we should probably research it today. It's a bit with the climate change, right? We should probably try to save our climate today instead of waiting until it's too late. So we want to do the same for cryptography. There are also 3 upcoming talks I want to advertise here a bit. I think, I don't remember the days, but the descriptions look pretty interesting, so I'm going to leave that up for a few seconds. So there's one on provable insecurity, one called Cryptography Demystified, and one about high assurance cryptography software, so I'm sure this is going to be interesting. Okay, let's return back to what I want to talk about. So there's something I jokingly call the post-quantum cryptography zoo. There are a few buzzwords up there, you don't really have to know what they mean. I'm just going to say them out loud: lattices, codes, multivariate polynomial systems, that's also a bit of a mouthful, hash-based cryptography, and there is the one that I want to briefly talk about tonight, called super singular elliptic curve isogenies. Okay, so this is the stuff that I really like. Isogenies, they're great. And now I'm going to tell you why they're so great. All right, so I don't know how many of you have a mathematics background. Maybe I can do a test. Can people raise their hands if they have some formal training in, say, algebra or, yeah, okay, so that's pretty good. So just gonna tell you something about it. So there are decimal numbers, this is pi. Then there are rational numbers, somehow they are 1/2, 1/3, and so on and so forth. Then there are the integers from -infinity to +infinity, and they follow nice whole steps. But for working with those numbers and for cryptography, we want something that's nicer behaved. We want somehow a finite set, okay? So this is just important for implementation. And the ones that we want to work with, I'm just gonna remind you, are the integers modulo n. So you take some positive integer n, big N, and then you consider the z from 0 to n-1, okay? And these numbers, they follow certain addition and multiplication rules, and it pretty much works like a clock phase, okay? I chose n is 12 here, And just bear with me, imagine my clock face goes from 0 to 11 instead of from 1 to 12, but it's really the same. Now, for example, if I try to add 10 to 5, okay, I start from 10, I go 2 steps, and then I arrive at 0. This is when my clock ticks over, right, like on a real clock. And then you go 3 more steps. And so 10 plus 5 more 12 is 3. So it's numbers that kind of behave this way. Think of addition on a clock face. And for the computer scientists out there, or I mean everyone probably knows about that, for a computer they are like the 8-bit integers where n is 2 to the 8, and then these are the numbers from 0 to 255, and so on and so forth. So these are the numbers that we want to work with. Just to set the stage a bit. And these isogenies, they will live in a world where we work with somehow related numbers to these integers mod n. And now for big N, we choose a prime, p, and then these integers mod p, they represent what we call the finite field with p elements, okay? And you can think of this as a set that has exactly p elements, and it really kind of behaves like the real numbers, okay? You can add numbers, you can subtract numbers, you can divide by everything but 0, okay? And this finite field with p elements works really the same. It's just a finite set, but everything is invertible except 0, okay? And these are the numbers that we're going to work with. And computers can do that, so that's fine. And just for the sake of telling you, there are also fields that have somehow p to the r elements, but they are not the same as mod p to the r, okay? But there is a way to construct it, but that's all you need to know about. So this is really the set of numbers that we're going to work over, and that's all you need to know. Okay, so the cryptographic problem that I want to focus in this talk is simple key exchange. I'm not going to talk about signatures, not going to talk about encryption, nothing. Let's just focus on this one simple problem of how do Alice and Bob exchange a key without anyone else somehow getting access to that key. And I mean, there are somehow classical solutions to that. I could put my key in a suitcase and I could bring it to Alice, or I could somehow pay someone to bring the suitcase to Alice. Or maybe people heard about that thing where I put my lock on the box and I ship it to Alice, and she puts her lock on the box and then she ships it back. And I remove my lock, and then I ship it to Alice again. Okay, so there are countless ways, but we want to somehow do this in a nice, instantaneous kind of way using mathematics. Okay, so this simple problem is what we're going to focus on. And classically, whatever that means for now, this has been solved by Diffie and Hellman, and this is this nice paper from 1979. The title is New Directions in Cryptography, so this already tells you that something important must be going on. And what they somehow invented there was a way to exchange keys between two parties using a nice, well-defined problem. Okay? And how does it work? Okay, I'm just going to tell you how it works. So there are two parties, Alice and Bob, A and B. They agree on a safe prime modulus n. Okay, so this is the integers mod n that we just saw. And the generator G. So what does that mean? Basically, in my set from 0 to n, I want to single out one element such that every element can be written as a power of that element. And somehow this means it generates it, right? So every y can be written as g to the x mod n. Okay, this is my setup. And then there's Alice and Bob, and they agree on these two parameters. Okay? And now, how do they do the key exchange? So it's very symmetrical. So Alice chooses a random a in the set from 1 to n minus 1. And she sends big A is g to the small a mod n to Bob. And as you might have guessed it, because I said it's symmetrical, Bob does the same. Okay, so how does the picture go? So Alice, on the left, she chooses a random small a, and she sends that big A to Bob. Bob chooses a random small b, he sends that big B to Alice, and then somehow they have to combine this somehow, right? And how did they do this? So this is nice. They compute the shared KK, the shared key. So Alice takes the B she got from Bob and raises it to the power of her own random secret value, and Bob does the same. And magically, through mathematics, they both get the same small k. And now I'm going to tell you why somehow this is hard for anyone else to get the same small k. So now bear with me. I'm going to write it down mathematically, first of all. I want to teach you a bit about that as well. So this is this diagram, this commutative diagram somehow that represents this key exchange that just happened. Okay, so Bob and Alice, they both start in the left upper corner with the G, and they both end up in the lower right corner, the G to the AB. So they both are able to somehow compute G to the AB, and no one else is. And how does that work? Well, Alice will only compute the horizontal arrows. So she only raises to the power of small a, because that's her random secret that only she knows. And Bob only computes the vertical arrows. So he only raises to the power of small b, because that's the secret he knows and no one else does. And I mean, by the commutativity and associativity of exponentiation, they just agree on the same g to the ab, which is cool. And somewhere in there hides a problem that we like to call the discrete logarithm problem. And it just happens for integers mod n if I choose my n appropriately. I'm not going to tell you how, but just believe me, if I choose it appropriately. If I give you y and g, for you it's hard to find the small x. It's somehow like taking a logarithm, and we call it the discrete logarithm because it's a discrete set of numbers instead of the continuous decimal numbers. What we started with was this discrete finite set of numbers. And this DLP is hard, okay? This is a hard problem for classical computers. And the best classic generic algorithm, I'm not going to talk about somehow algorithms that specifically target integers mod n. I'm just going to talk about generic algorithms for this DLP problem. The best algorithm somehow has runtime square root of big N of the number of elements. And say I chose my n about the size of 2 to the small n, so n bits, then solving this takes exponential time in n, right? Because the square root of 2 to the n is still pretty big. Okay, this is about 2 to the n half, and if I make n, I don't know, 1,000, it's still 512 bits. So this is a hard problem. But recently there has been a record for factoring and DLPing over a 795-bit modulus. And they used a bit of a better algorithm, but still, it still took them a long time. Okay, so if I remember correctly, this feat took them 4,000 core years on a 2.1 gigahertz computer. I mean, it's still 4,000 core years. So this is a long time. Okay, but as you can see, it's possible to solve this. I mean, if I just put enough, if I have a big enough hammer, I can solve this. Okay, but again, you can make n pretty big, bigger than anything being able to solve this anymore. But, okay, so there's a quantum algorithm for this. And this is this other paper from '95, Peter Shor. So he thought of this algorithm that solves the DLP in polynomial time. Okay, now remember our big N, we took about 2 to the small n, and this Shor's algorithm only takes small n to the cube. And I mean, if n is 100 cube, it's not that big. And I can make n 1,000, but 1,000 cube is still not that big. Okay, so there is a good algorithm that assumes the existence of a quantum computer. I mean, as outlandish that might sound, but still, this algorithm in theory breaks the DLP. Okay, so I don't know, maybe in 20 years or in 30 years or 100 years, I don't know personally, but if there's a quantum computer eventually that somehow runs this thing, okay, DLP is broken, classically. So, well, what to do? As I said, let's just try to come up with cryptography for which we don't know a quantum algorithm, okay? Or for which we expect that there won't be a quantum algorithm ever. There are a few candidates. Again, there's this SU, lattices, codes, this long word, and isogenies, okay? Now, what I want to tell you about is what is an isogeny and how do I do key exchange with an isogeny, okay? Because I don't know, it's a fancy word, but what does it mean? Okay, and there was this other word that started with elliptic curve isogenies. So probably I should tell you about what is an elliptic curve, or give you a remainder if you've seen this before. So I look at this equation in two variables and two constants. The variables are x and y. My constants are a and b, and the equation is y squared is x cubed plus ax plus b. And now what I want to look at is all the solutions to this equation, all the possible pairs y and x or x and y. And of course they're going to look different somehow for the different possible numbers that I can plug in for x and y. And again, you might have guessed it. First of all, we're going to look at it over the decimal numbers, and then later we want to consider this again over our finite field, okay? Because we like we like this discreteness. And over R, a simple equation, I just chose some values for A and B is set to 0, A is set to 1, A is set to 0, B is set to 1. The solution set looks like this. And actually it extends infinitely far on the right side, up and down. Okay, so this is just somehow a snapshot of what the solution set looks like. But over my finite field, and I chose one with 101 elements, it looks like this set of points. Okay, so elliptic curves look differently over different fields, but that's fine. That's fine. Okay, now quick reminder of why people like elliptic curves. So there's something called the point addition law. So I can take 2 points on this curve and I can somehow add them. Okay, but this is not really addition in the sense of numbers. There's somehow a law that I have to apply, and let me quickly show off how this is done. So how do you add 2 points on this curve? Well, you take these 2 points, you put a line through it, and then there is a law that says that if I put a line through 2 points, then this line has to cut the curve in the third point. Okay, so I put the line through these 2 points, it cut the curve in the third point all the way up on the right, and now what I'm going to do is I'm going to reflect the point down on the x-axis. Okay, so I draw this other line, I reflect it down, and then what I define is that other cut. This I define to be the sum of these 2 points. Okay, so and that works. Okay, I can add point, I can subtract points. There will be inverses. So this kind of like acts like integers mod n when you only consider addition. Okay, kind of. It's not really the same. But you can also single out a special point O, like beautiful O. We call the origin, whatever that is. And this origin kind of acts like a 0. So if I add the origin to a point, well, I get the point again. Or if I add the point and its inverse, I get that point, I get 0. Okay, so there's something like a 0. And you can also multiply points, right? I mean, what is multiplication? It's just repeated addition. So in brackets n, this is what I write for point multiplication. Just add the point n times to itself. Okay, so there's nothing fancy going on here. So you can somehow add points, you can multiply points. That's pretty cool. And if you look closer, you can look at this special set here that are denoted E brackets big N, and these are all the points on the curve such that if I multiply this point by n, it gives me 0, okay? And this set, for the mathematically inclined people among us, I will say this is somehow the n torsion of the elliptic curve, whatever that means, but if you're interested, you can look it up. This set kind of acts like additive integers mod n, like 2 copies of it, okay? And now this is where the term supersingular comes from, one of the definitions. This is not the only definition, but this is one of them. If you look at the elliptic curve, not over the reals, okay, or over which other numbers, but over this finite field, and if you look at the p torsion, then this behaves differently for different types of curves. Okay, the p torsion is either empty, and then we call the curve supersingular, or it's just one copy of integers mod p, and then we call it ordinary. Okay, it's not really important to know what that means. It just means that there's a distinction for curves somehow that's somehow ingrained mathematically deep down there. And because this n torsion is somehow 2 copies of integers mod n, additive integers mod n, I can generate it by taking linear combinations of 2 points, say p and q. And these are like the generators we saw earlier, right? But these are now additive generators instead of somehow exponential generators. But everything behaves kind of similar. And now you can use this to do cryptography already, if you wanted to, right? You can somehow look at the DLP in that group. But there's the problem again that the DLP in there's Shor's algorithm again, right? So even if you do cryptography in this group, you run into the same problem. Okay, so we have to do a bit better. We have to search further. And this is where isogenies come into the play. So one way you can think of an isogeny is remember how we found the integers mod n by somehow dividing Z by all the n multiples. And you can do something similar with an elliptic curve. You can somehow take part of this n torsion And you can divide an elliptic curve by this. You can mod it out. And it turns out this is mathematically well defined, and it gives you another elliptic curve. Okay? So I take a curve E1, I take a part of my end torsion, I divide elliptic curve E1 by G, and I get another elliptic curve E2. And there's something else that comes along with this construction, and this is what we call the isogeny. This is a map, okay? Along with this construction comes a map from E1 to E2, and this map is what we call an isogeny. So for us now, an isogeny is just a map that takes us from one curve to another curve, okay? And this map is kind of special because it behaves in a nice way, and it plays nicely with the structure that's already ingrained on our curve. Namely, I can either add 2 points on my starting curve and send it through that map to the other curve, or I can take 2 points on my starting curve, I can send it through the map and add it over there, and it gives me the same thing. Okay, so this map somehow behaves nicely with point addition. That's pretty nice, just as a side note. So this map is special. So this is just a remainder of what I said. Adding points on E1 and sending the result to E2 is the same as somehow sending points to E2 and adding them there. So this map somehow plays nicely with my laws on my elliptic curve. And now I have to make a definition. So in mathematics, we call the kernel of a map. We call that the set of all the inputs to the map that are sent to 0. Okay, and we saw this origin O here that acted like 0. So the kernel of my isogeny I'm just going to define as all the inputs to the isogeny that are sent to the 0 on the other curve. Okay, and in written notation, it's the set of all P on E1 such that the map of P is 0. And it turns out that this kernel for my isogeny that I started out with somehow recovers this part of the end torsion that I used to construct it. Okay, so there are somehow 2 ways now to think of an isogeny. So this is what we started with. We considered E1 mod G, and it gave us this map from E1 to E2. But if I start with this map from E1 to E2, we also find that G again. Okay, so somehow there are 2 ways to represent this map. We can think of a subgroup, this G, or we can think of the map. And ultimately, somehow there is a correspondence between the various subgroups for different n and isogenies that are somehow emanating from a curve. You can think of this like all the hairs on my head, they're going out, and then they're going to reach other elliptic curves maybe. And these notions can be used interchangeably, so somehow there's a correspondence. And again, I can choose different n's, okay? So somehow from one curve, I can have many outgoing isogenies that are different in a sense. And now the thing is, in practice, we actually want to compute with these maps. So right now, this is just general abstract nonsense. I didn't tell you anything of how to compute with these things. I just told you there are somehow correspondences, but I mean, what does it even mean, right? It's useless if I can't use it in practice. And then there's another thing. You can compute these things. There are formulas. People have worked on this, but somehow the cost grows if I enlarge an n. Okay, so really in practice, for applications, I want to choose small n. Okay, maybe 2 or 3. That would be pretty good. And now the thing is, it's the supersingular curves for which I can somehow control or choose the possible n's very easily. Okay, so this is the reason why we consider supersingular curves. And now I can choose my prime to be of this form, and then magically this is going to force 2 and 3 being possible. Okay, so this is the reason why we choose supersingular ones. There's some theory which is not interesting for you, but it's just it's important for implementation, and there's a way basically for us to force the curve to have those isogenies that we like. But there is another important reason, okay, and this is the reason that actually makes it interesting for cryptography. So what I can do is I start with an arbitrary curve, and this might not be a supersingular one, just any curve, and say I consider all the outgoing 2 isogenies, if these are possible, for n is 2. So there's going to be 1, 2, and 3, And then again, from E1, I can again consider all the outgoing isogenies, and so on and so forth. So what's going to happen here is this is going to generate a graph where the vertices of my graph are elliptic curves and the edges are isogenies. Okay, so somehow behind the scenes there's this graph hidden. And now turns out that if you do this for a supersingular elliptic curve, and then I generated this yesterday for you. So this is one possible graph. I can't remember which prime I took, but here you can see all the ellipses are elliptic curves, and all the edges between them are two isogenies. So this is an example of a supersingular two isogeny graph. Okay, this looks pretty wild. So I can do the same for, say, n is 3, if it's possible, or n is 5, and so on and so forth. So there are many, many graphs hidden. But why is the supersingular graph specific and important? Well, it turns out that somehow the supersingular one is connected, and it's what we call a Ramanujan graph. Okay, and this is, I'm going to explain this in a second. And as a bonus, for implementation purposes, it turns out that you can do all your implementation in arithmetic in the finite field with p-squared elements. This is nice. Okay, so I'm just going to say that if you don't consider supersingular elliptic curves and you go along these graphs, then what's going to happen is that somehow this field of definition, what we call it, could grow for you to be able to go further. But that would suck for implementation, okay? But supersingular ones is nice, so fp squared is enough for us. So this is again, is good for implementation. So somehow magically, many, many things happen here that are benefiting us. And again, why is it nice that this is a Ramanujan graph? So a Ramanujan graph has certain optimal expansion properties. And this means that if I start from a random point in my graph and I take a random walk with somehow log many steps of the total amount of vertices, then this will put me in a very uniform place in that graph, okay? And this is good for cryptography, okay? Because you only need to take log many steps to somehow randomize yourself in that graph. And this is what this could look like. So I started at that red ellipsis over there. This was my starting point. And then I generated a few random walks, and the blue points are where I got placed. And I mean, this might not prove anything, but it gives you an idea of how somehow uniformly it places me around that graph. Okay? So it's good for cryptography, but there are other reasons. So supersingular elliptic curves, somehow I can actually compute how many of these curves I will have in my graph. So this is another reason to be looking at these things, because if I don't even know how many curves are in my graph, well, I can't really say anything about the security, but at least for supersingular ones, I can say they're roughly p over 12 many. Okay, and then again, if I choose my p about n bits, well, then I will know that my graph has about 2 to the n elements. And at least there I can say something about the cryptographic strength, right? I can make n big, and then you can say, oh yeah, you have this random graph, you take some n length walks, and then it places you randomly in there, and your whole graph has about 2 to the n elements, and then I can say something about the expected runtime of my algorithms, right? So this is another reason why we want to consider supersingular curves, because I can tell you how many elements are in this graph. Okay, so a quick summary of what we saw, why this is nice. So what you get is somehow a compact representation of an L+1 regular graph, and we saw examples, for example, L is 2 or L is 3. Bigger values are possible, but we don't even care about those because this is what gives us the fastest somehow arithmetic, such that we can work over fp squared. This is nice. This keeps our implementation fast. I can tell you how many vertices are in my graph, about p over 12. And again, such that the graph has somehow mixing properties that are useful for cryptographic applications. So because I want to use this ultimately for cryptography. And again, that's what we said. If I choose an n-bit prime p, then the graph has about 2 to the n vertices. So exponentially many vertices. And turns out that there are some hard problems that I can ask you to solve in this graph that don't have good quantum algorithms. So one hard problem is this. I take two supersingular elliptic curves. So I just give you two random curves in this graph, and I ask you, find an isogeny path between those of two isogenies or three isogenies. Okay, and it turns out somehow that this doesn't have good quantum algorithm. So classically, I mean the numbers are not super important here, but classically the complexity is p over p, the fourth root of p, and the best quantum algorithm is a bit better. But it's not super important what's there. What's important is that there is no polynomial time algorithm compared to our DLP that we started with. Okay, so if I make this p very large, your quantum computer, your hypothetical quantum computer will probably not solve this. Okay, so that's cool. So how do we do key exchange? So I start with a supersingular elliptic curve E, where I chose my prime P, such that 2 and 3 isogenies are possible. And then Alice, earlier remember she chose a random number A, but now Alice will choose a random subgroup big A, and she will send E mod A to Bob. Okay? This amounts to Alice for computing an isogeny. And again, this is a very symmetrical key exchange, except that now Bob won't use the same generator, but Bob will use the 3 isogenies. Okay? So Bob will choose a random subgroup B, and then he will compute E mod B and send this to Alice. And this is the picture. There's Alice, there's Bob. Again, Alice chose A, Bob chooses B. Alice sends E mod A to Bob, Bob sends E mod B to Alice. And then how do they somehow agree on a shared key? Well, the way they're going to agree is they will just mod out by their respective subgroups again. And turns out the elliptic curve that they find is going to be the same for both of them. Okay, so how does that work? Again, let's return to our graph. So say Alice and Bob, they agree on the black curve. Okay? The black curve on the left side. And then Alice will compute these red steps, which correspond to taking a subgroup. So Alice will compute these red steps for her secret subgroup, and she will end up at the red curve in the upper right corner. And Bob will do the same, but now Bob is not in the 2 graph, but in the 3 graph. So this is the 3 graph. And the black curve that they started from in the 3 graph is down there, and he will also select a random subgroup, compute the secret path, and Bob will end up in a blue curve. And now Alice will send her red curve to Bob, and Bob will send his blue curve to Alice. And then Alice will consider the blue curve in the 2 graph. Okay, so Alice, she starts from the blue curve that she got from Bob, and this is the position in the 2 graph. And again, she computes that same secret path and ends up in the green curve, which is up there. Bob got the red curve from Alice, so Bob, he has the red curve there, again, computes that path, and then ends up at the green curve. And it turns out that the green curves here and there, they are the same. And this is going to be the shared key for them. This is SIDH. Okay, this is how you exchange a secret key using this supersingular isogeny graph. And that's somehow the whole magic. And again, let's compare these two things a bit, the DLP-based one and the SIDH one. So we had this square where Alice and Bob started in the upper left corner and again ended up in the lower right corner. And now SIDH looks very similar. Okay? So Alice and Bob start with this common curve E in the upper left corner. Again, Alice computes only the horizontal arrows because she knows her secret group big A. Bob only computes the vertical arrows because only he knows his secret group big B. And again, they both end up in the lower right corner where they find a shared key. But now in this case, the shared key is not this element G to the AB, but an elliptic curve. But again, there's a mathematical way somehow to attach a unique number to it. So it's a solved problem to somehow actually make some bytes out of this. And yeah, that's SIDH. That's everything. This is a nice example of a post-quantum somehow cryptography scheme that we have today. And now let me finish with a quick conclusion. So I showed you the SU. There are several candidates somehow for post-quantum cryptography. And among of them, are some schemes based on supersingular elliptic curve isogenies. And we've seen that we know some hard problems involving these isogenies that are somehow hard for quantum computers, which makes this one possible scheme for somehow a quantum computer world, okay? And probably I should say that we don't envision a world here where users like me or you are in possession of quantum computers. Probably what we think about is somehow that state actors are in possession of quantum computers, right? So this is even more important for us to be looking into these things. And what we saw was somehow to perform a Diffie-Hellman-like key exchange using these isogenies. But, and this is what I didn't tell you about in this talk, there are also schemes for signatures based on isogenies. There is a scheme for key encapsulation based on isogenies. So there are other possible candidates for other somehow cryptographic building blocks based on isogenies and these hard problems. And if you're super interested about this, you can either ask me or come to our assembly. And if you like reading somehow scientific papers, papers about isogenies and cryptography in general, you can find this on the ePrint archive. Okay, so this is a web page where people post preprints about their papers, and there's a huge collection about, among of them, isogeny papers. So if you're interested in this is somehow the place to research. Okay, and with that, I would like to thank you all for your attention. Okay? Oh, okay. Yeah.
Yeah. Is there any question? Okay, I got the signal angel there doing some Morse code.
Yes. Can you recommend any literature for the theoretical background?
The theoretical background. There are a few papers that are nice. Okay, the question again was literature about theoretical background. And yes, there are a few papers that are giving some nice, even theoretically involved summaries about the background. And your best bet is to go to ePrint and you enter isogenies in the mask of search terms or SIDH, and you look at the papers that somehow say maybe a short introduction to isogenies, something like that. I mean, you will find them if you search for them. I don't know them from the top of my head, but they are out there for sure. Yeah, and thanks for him. So there is a very recent paper by Craig Costello, also somehow titled The Short Introduction, something like that. Yeah, so this is also maybe a good source for you to look at.
Yeah, isogenies for beginners.
Isogenies for beginners, thank you.
Yeah.
Hello. Oh, yeah. So you've used elliptic curve as an algebraic group, right, to compute these isogeny graphs. So why do you use elliptic curves? What's the properties of elliptic curves as a group? So could you use any group to compute these graphs, and could you use these as the basis for your scheme, for your key exchange scheme?
Okay, so the question was why use elliptic curves and the group structure that they impose to look at isogeny graphs involving elliptic curves, and whether I could use maybe other groups. And actually, there's a twofold answer maybe. So if I go back, or actually let me go to my backup slide, which gives you SIDH in its full glory, you can see there's some extra information being sent, namely these generators for my group. And actually the same commutative diagram for SIDH, you could in theory compute using another group as well that has the proper subgroup structure. But the graph that you will find is probably not going to be interesting. Okay, I mean, it's really, really somehow that Richelieu property that makes the graph interesting for cryptography. But yes, in theory, the SIDH commutative diagram, you could also compute for other groups, yes.
Okay.
Okay. How good are classical algorithms that try to reverse that SIDH problem? Because that will be the bound for how large your keys have to be secure.
Yes, so the question was how good are classical algorithms? And again, I said I think the runtime for those is square root of p. And this tells you how big you have to choose p. Yeah.
And how confident are you that this really is hard for a quantum computer as well?
Well, how confident am I that this is really hard for quantum computers? So first of all, cryptography is all about confidence, right? So someone proposes a problem, this problem gets cryptanalyzed, and if it's not broken after 40 years, then people will say, oh yeah, I'm pretty confident this is good. And maybe if the NSA doesn't tell you anything about it, or maybe if they don't have, anything on it, then you can also say that you're confident in it. But I think this is really an answer that only time. This is a question that only time can answer, right? I mean.
Yeah, I have a question from the signal line.
Yeah. Is it possible to prove that no polynomial time algorithms for the isogeny problems can exist for a quantum computer?
Yeah, that's a good question. How do you prove that no algorithm exists? This brings us into territories like I don't know. Yeah, no. let's not do that.
Microphone one.
Good talk, by the way. The last slide, you say that this is hard for a quantum, but that can't be true because we don't even know if any algorithm is hard for classical computers, right? So I'm guessing you're saying that intuitively it feels hard, yes. Which is the same intuition we might have about like factoring and
exactly.
so on. So you mentioned there's multiple candidates for post-quantum cryptography, and they all intuitively feel hard somehow. Do you know if this specific candidate, would this be your horse in a race? Like, is there anything about this specific way that you think would be the best fit for post-quantum cryptography?
Okay, so your opinion is very valid. Of course, we don't know if it's hard, right? This again connects back to the other questions. How do you trust something like that? Again, people do cryptanalysis for 40 years or whatever, and then you say, well, no one found anything, it's probably hard.
Right, but it hasn't been 40 years
for
this.
Exactly, you cannot say that. These things are relatively new. And personally, I'm not gonna, believe in any of these things until some time passes. So my reason for looking into these things really is more somehow a mathematical curiosity, because I think these things are beautiful. And somehow the cryptography that arises from it is more of a side effect for me personally. So I'm not gonna put out any somehow, guesses on which of these things is actually gonna win the PQ race or whatever. Yeah.
Hi. You showed or said you think it's hard for the classical way and for the quantum cryptography way.
Mm-hmm.
I think I just read a paper like last year about a combined way doing classical and quantum cryptography combined, which outperforms either one of those ways. Do you think this could also be can be relevant or make this one way put in computable in polynomial time?
So are you talking about an algorithm that somehow combines a classical step and a quantum step to break this? Yeah, well, I mean, most algorithms somehow that we say use a quantum computer involve a classical part anyways. I mean, if you think about Shor's algorithm, there's a classical part and a quantum computer part. So I'm not sure which algorithm you read about, but I'm sure that somehow all the quantum algorithms involve a classical part implicitly anyways. Yeah. So, yeah.
Signal Angel.
Yeah. Can you please name the mentioned contestants in the NIST challenge based on isogenies?
So there is Psych, I believe. super singular isogeny key encapsulation, but I don't really follow the NIST thingy closely, so I actually couldn't even name all the names that are involved in it. But you can look it up on the NIST website, and I believe somewhere there is also a classification of the contenders into the SU. So they will tell you which contenders are based on lattices and which contenders are based on codes and which ones are somehow based on isogenies. But off the top of my head, I don't even know. No, sorry.
Microphone one.
If I got everything correctly, those isogenies are group homomorphisms between the elliptic curve and the factor group of the elliptic curve by G, and which has kernel G again.
Yes.
And you said that finding the isogeny path in the graph is rather difficult, but wouldn't the real difficulty rather be finding the subgroups G? Because group homomorphism between the elliptic curve and the factor group with kernel G is simply the canonical projection.
Exactly. So I see you are mathematically trained, which is very nice. And I appreciate
math,
that.
yeah.
This is great. And I'm very happy about that. And yeah, if you look at this slide, actually, so the secrets are these alphas and betas, which somehow determine the subgroup. And yes, so finding the isogeny path is equivalent to finding the alpha somehow that generates this group. And as you said correctly, finding the isogeny path is somehow finding this group. But it's just somehow restating the problem, but it's still hard somehow to find this subgroup. Yeah.
All right, thanks.
Thank you. Very cool.
Microphone 2.
Okay, thank you for the great talk. So can you play this game a little bit further? I mean, can you choose higher dimensional abelian varieties to make it even more secure, or is it just absolutely inaccessible? Like, I mean, from the computation perspective, like the choice of field of definition is difficult, for example. So,
okay, so the question was on whether you can use higher dimensional abelian varieties, and maybe for the people who don't know what that means, somehow you can attach a dimension to these things, and elliptic curves somehow have a dimension 1 attached to them. And the question one was, can you somehow look at dimension 2 or dimension 3 or higher? And actually, back in the days when people were thinking about the DLP problem on the points of elliptic curves that I mentioned briefly, people had the idea of maybe using dimension 2 or dimension 3, but it turns out somehow that this DLP problem actually at some point gets easier in higher dimension. Okay, so classically, if you look at the DLP, you somehow want to stay at dimension 2. But now what you can do, of course, is you can look at isogenies between dimension 2 or dimension 3 ones. And actually the problem that arises there, and this makes elliptic curves very special, is that we can compute isogenies rather efficiently for elliptic curves because of Belou's formulas. Okay, so somehow this gives us a very direct means of computing these. But it actually gets hard as the dimension grows. For example, for dimension 2 already, the only isogenies that I somehow am able to efficiently compute are 2 and 3 isogenies. So there are some packages out there that can compute higher ones, but only if my prime is very small. And for dimension 3 and higher, it gets even harder, okay? And then there's another thing that comes into play. So dimension 2 varieties, somehow they all arise from what we call hyperelliptic curves. But if you look at dimension 3s and higher, then somehow, sometimes you land at the point in your graph that does not come from a hyperelliptic curve anymore. So there is another complication. So, I mean, I had a friend who was looking into genus 2 isogenies, and it's possible to do there, but I don't know. I think personally this is more of a toy than something that's good in practice. Yeah.
Can you use this scheme to implement a fully homomorphic encryption scheme, or is it already?
No. No. Yeah. No, fully homomorphic encryption is somehow a pipe dream. But, I mean, sometimes it's possible. So the idea is somehow that you can add ciphertexts and get the sum of the ciphertexts and have a second somehow operation. Namely, you should be able to multiply ciphertexts and get the multiplication of those ciphertexts. But we didn't even talk about encryption. Okay, so...
Yeah.
Another question, is there any crypto primitive used in the isogeny approach that cannot be stark reduced to finding a hidden subgroup in an abelian group?
Could you repeat the question, please?
Is there any crypto primitive used in the isogeny approach that cannot be stark reduced to finding a hidden subgroup in an abelian group?
Okay, so this, I think, this question tries to connect back to somehow maybe the hidden shift problem or the hidden subgroup problem and Kuperberg's algorithm, but I think I'm not able to answer that question now without talking to the person that actually asked it, because it's a bit vague, so I'm sorry about that.
How do you send an elliptic curve over the wire?
Yeah, maybe I should answer that actually. So we saw the parameterization of the curve that had these coefficients big A and big B, but what I didn't tell you is that to an elliptic curve you can actually attach what we call an invariant in mathematics. And for an elliptic curve, this is is called a J invariant. It's a single integer which somehow determines this elliptic curve uniquely. So if I want to send an elliptic curve, I can simply send you its J invariant, and if you know the field of definition, you're going to be able to somehow recompute it just from this single value. So it's actually quite a compact representation, which makes this also interesting.
This isn't.
Yeah.
I guess this is all. Thank you.